This is Colin Selleck of Binghamton University. This video lecture is from chapter 16.1 through 16.3 of the book Dynamics by R.C. Hibbeler. Today's topics include planar rigid body motion, translation of a rigid body, and rotation of a rigid body about a fixed axis. Today's objectives: you will be able to analyze the kinematics of a rigid body undergoing planar translation or rotation about a fixed axis. Activities: we'll go over some applications. Talk about the types of rigid body motion, talk about planar translation and rotation about a fixed axis, and then we'll solve some problems. So here's a ride in an amusement park. These passengers are subjected to curvilinear translation since this vehicle moves in a circular path, but they always remain upright. If the angular motion of these rotating arms here are known, how can we determine the velocity and acceleration experienced by the passengers? Gears, pulleys, cams, these rotate about fixed axes, and we often use them in machinery to generate motion and transmit forces. The angular motion of these components must be understood to properly design the system. So first, let's define rigid body motion. So far in this course, we've only considered the kinematics and kinetics of a particle. A particle has mass, but negligible size and shape. So there are cases where an object cannot be treated as a particle. In these cases, the size or shape of the body must be considered. Rotation of the body about its center of mass requires a different approach than simple particle mechanics. Now we're going to start to study rigid body motion, and we're going to limit this to planar motion. A body is said to undergo planar motion when all parts of the body move along paths equidistant from a fixed plane. So there are four types of planar rigid body motion. The first type is rectilinear translation. So the body moves along a straight path and it does not rotate. So a line on the body stays in its same orientation as you see here. The second type is curvilinear translation. In this case, the body is moving along a curved path, but a line on the body does not change, so it is not rotating. The third type is rotation about a fixed axis. Here you can see this rigid body is rotating about a fixed axis. And the last type is general planar motion, where the body both translates and rotates. So let's look at some examples of those four types. Here's rectilinear translation. This piston moves back and forth in one direction only inside the cylinder. This pulley right here is moving around a fixed axis that you see here. This linkage right here is undergoing curvilinear translation. You notice that the radius of this crank and the pulley are the same. So there's no rotation of this link, but it is translating. And this link here is undergoing general planar motion. It is both rotating and translating. So here we have a rigid body in blue. There are 2 points in the body, A and B. And the position vectors RA and RB from some fixed coordinate system. The X prime, Y prime system is translating. So we can write that RB is equal to RA plus RB with respect to A. It's just vector addition. So we can take the derivative of this equation and say that the velocity of point B is equal to the velocity of point A plus the velocity of point B with respect to A. However, the velocity of B with respect to A is 0, right? They're both in the same rigid body, and we're in pure translation, so they have the same velocity. Therefore, in this case, the velocity of B is equal to the velocity of A. Now again, this is for translating rigid bodies. And likewise, we can say the acceleration of B is equal to the acceleration of A. So all points in a rigid body subjected to translation move with the same velocity and acceleration. Now we'll talk about rotation about a fixed axis. So here in blue, we have a rigid body that's rotating about this axis here. We have a point P on the body, and it's located a distance r from the axis of rotation. The position of particle P is denoted by this angle theta. When a body rotates about a fixed axis, any point P in the body travels along a circular path. So as this body rotates, it undergoes some small displacement d theta. So we can say that omega is equal to d theta dt. Now we're defining omega. Omega is called the angular velocity, and we measure it positive counterclockwise. Likewise, we can say that omega is changing with respect to time. We call that angular acceleration. So angular acceleration is a derivative of omega, angular velocity with respect to time. Omega has units of radians per second. Alpha has units of radians per second squared. Now you can compare this to what we did earlier with velocity and acceleration. This is very similar. Instead of distance changing with time, we have an angle changing with time. We also measure alpha positive counterclockwise. Now if the angular acceleration alpha is a constant, we can use the equations for angular velocity and acceleration. These are integrated to yield the set of algebraic equations before. So this is very similar to constant acceleration and rectilinear motion. So omega is equal to the initial omega plus the constant angular acceleration. Remember, this is only good for constant angular acceleration times time. And theta is equal to initial theta plus initial omega times time plus 1/2 angular acceleration times time squared. And likewise, omega squared is equal to initial omega squared plus 2 alpha angular acceleration times theta minus theta naught. These should look familiar to you. These are very similar to the constant acceleration equations for rectilinear motion. Theta naught and omega naught are the initial values of the body's angular position and angular velocity. So now we've defined what angular velocity and angular acceleration are. Now we're going to talk about the velocity of a point P on a body. So here we have a rigid body in blue. It's rotating about a fixed axis that you see here. And here's a top-down view here. And we're interested in what the velocity of this point P is. So this is a top-down view of this body. So it's rotating with some angular velocity omega. So if you look at this area right here, we can see that the length ds is equal to r d theta. So I can divide that by dt on both sides. ds dt is velocity, radius, and d theta dt is omega. So the velocity of this point P is equal to r times omega. So it's just the radius from the fixed axis to the point times omega. It's useful to write this down in vector formation. You have this vector r sub p, and it goes from a point on the axis of rotation to the point P. Well, I can say that velocity of point P is a vector is equal to the cross product of omega cross r sub p. Now omega is a vector, and when we study planar motion, omega is going to be in the k direction as well as alpha. And remember, we use the right hand rule to determine the direction of the velocity. So now we're going to talk about the acceleration of a point P on a rigid body. It has two components, as you might suspect. It has the tangential component and a normal component. Now this rigid body is rotating. It has some omega and some alpha. Now the tangential acceleration is going to be equal to the angular acceleration times r. It's very similar to the velocity of point P is equal to omega times r. In this case, the tangential acceleration of point P is equal to alpha, the angular acceleration, times r. And the normal acceleration is equal to omega squared times r. So that's a centripetal acceleration. These equations should look familiar to you. They're very similar, again, to the rectilinear equations. Now the tangential acceleration component, a sub t, this one, that represents the time rate of change in the velocity's magnitude, and the normal component represents the time rate of change in the velocity's direction. It is always directed towards the center of a circular path. So continuing our discussion on the acceleration of point P on a body undergoing rigid body rotation, the vector formulation of those two previous equations, the velocity of point P is equal to the cross product of omega cross r. So the acceleration is equal to the time derivative of the velocity. So we can say that is d omega dt cross r plus omega cross derivative of r with respect to time. And this simplifies to the acceleration is alpha cross rp plus omega cross r. This is the tangential part of the acceleration. This is the normal acceleration. And the magnitude of a, of course, is the square root of the sum of the squares. So let's establish a procedure when you want to analyze a problem that has rotation about a fixed axis. First, establish a sign convention along the axis of rotation. If a relationship is known between any two of the variables, alpha, omega, theta, or t, the other variables can be determined from these equations that you see here, and these should look familiar to you. These are very similar to velocity is ds dt, acceleration is dv dt, and ads equal vdv. If the angular acceleration alpha is constant, we can use the equations for constant angular acceleration. To determine the motion of a point, we can use these scalar equations you see here. The velocity is omega times r, the tangential acceleration is alpha times r, normal acceleration is omega squared times r. Alternatively, you can use the vector form of these equations, and this is probably a good way to go in a lot of problems. As long as you get the signs right initially, they'll come out right at the end. Okay, let's do an example. We have this motor here, and it's turning a gear A with a constant angular acceleration. Alpha sub A is 4.5 radians per second squared. So that's constant, so we can use our constant angular acceleration equations. It starts from rest, so that means the initial omega is 0. The cord you see here is wrapped tightly around the pulley D, which is rigidly attached to gear B. Find the velocity of the cylinder C and the distance it travels in 3 seconds. So our plan is we need to relate the angular acceleration of gear B and pulley D. We need to relate those to alpha sub A. And the acceleration of cylinder C can be determined by using equations of motion for a point on a rotating body. Since the tangential acceleration at point D right here is equal to the acceleration of the cylinder A sub C. And then we can find the velocity and distance of C by using our constant acceleration equations. So at this point P, where these gears mesh, where gears A and B mesh, they're going to have the same speed and tangential component of acceleration. So therefore we can say that tangential acceleration is equal to alpha A times RA. And alpha A is 4.5 radians per second times R, which is 75 millimeters. And likewise, we can say that the angular acceleration of gear B times its radius, which is 225. That's also the tangential acceleration. So we can set those two equal to each other and relate the angular accelerations of gears A and B. So 4.5 times 75 is equal to alpha B times 225. So the angular acceleration of gear B is 1.5 radians per second squared. Now, since pulley D is rigidly attached to the gear B, we can also say that the angular acceleration of D is equal to the angular acceleration of B. And also, assuming that this cord does not slip, it's inextensible, the velocity and acceleration of the cylinder C will be the same as the velocity and acceleration of this point P prime. So we can say that the acceleration of C is equal to the tangential acceleration of that point P prime, which is the angular acceleration of D times the distance to that point RP prime. So this is the angular acceleration of pulley D is 1.5 radians per second squared, and the distance between the axis of rotation and that point P prime is 125 millimeters. And we'll change that to meters. So the acceleration of the cylinder C is 0.1875 meters per second squared. So since the angular acceleration of A is a constant, the angular acceleration of pulley D and the acceleration of cylinder C are also constant. So therefore we can use the constant acceleration equations for rectilinear motion and apply those to cylinder C. So we'll say at t is equal to 3 seconds, you can say that the initial conditions S0 and V0 are 0, and that's of the cylinder C. For constant acceleration and rectilinear motion, the velocity of C is equal to the initial velocity plus the acceleration times time. So we'll say the initial, what started from rest, initial velocity is 0, the acceleration of C was 0.1875 meters per second squared times 3 seconds. So the velocity of C after 3 seconds is equal to 0.563 meters per second, and it's upwards. We're also asked to find the distance that that cylinder travels in 3 seconds. So we can use our constant acceleration equation for distance. It's equal to the initial displacement plus initial velocity times time plus 1/2 times the constant acceleration times t squared. So in our case, the position of the cylinder C after 3 seconds is equal to 0 plus 0 plus, it started from rest, so V0 is 0, plus 1/2. The acceleration of C is 0.1875 meters per second squared times time squared, 3 squared. So in 3 seconds that cylinder has moved 0.844 meters upwards. So here's another problem. We have these two gears. Gear A has an angular acceleration of 4t cubed radians per second squared, so it's a function of time, and t is in seconds. And the initial omega angular velocity was 20 radians per second. Find the angular velocity and angular displacement of gear B when time is 2 seconds. Our plan is to apply the kinematic equation of variable angular acceleration. So the previous problem we had constant angular acceleration, but now the angular acceleration is a function of time, right? It's 4t cubed. So we want to find the angular velocity of gear A and also find the relationship of angular motion between gear A and gear B in terms of time. And then we'll plug in t is equal to 2 seconds. So here's a nice close-up of the two gears. The initial angular velocity of gear A is 20 radians per second, and then this variable acceleration is applied to it. And the radiuses are shown here, 0.05 meters and 0.15 meter. So we were told the angular acceleration is 4t cubed radians per second squared. Well, alpha is equal to d omega dt. So we can write that alpha dt is equal to d omega. So making those substitutions, flip this equation around. D omega is equal to, from omega naught to omega, is equal to the integral of alpha, which is 4t cubed dt. And we'll say that goes from 0 to t. So this becomes omega minus omega naught is equal to t to the 4th. So omega as a function of time is t to the 4th power plus omega naught. Now we also know that omega is equal to d theta dt. So d theta is equal to omega dt. So I have omega as a function of time here. So I can say the integral of d theta from theta naught to theta is equal to the integral of omega, which is t to the 4th plus omega naught dt, evaluated from 0 to t. So when you do this integration, it comes out that theta is equal to theta naught plus 1/5 t to the 5th power plus 20 times t. So now we have these two equations for theta and omega as functions of time. So we were asked when t is equal to 2 seconds, so we can plug 2 into equation 1 and come up with 36 radians per second. And theta at 2 seconds is equal to 46.4 radians. So just like in the first problem, since these gears mesh at this point right here, we can say that the velocity is the same. So omega A times RA is equal to omega B times RB. So angular velocity of gear B is equal to omega A, which is the angular velocity of gear A, times the ratio of the radiuses. So the radius is 0.05 divided by 0.15. And likewise, we can say that theta of B is equal to theta of A times the ratio of the radiuses. So we make the substitutions, and omega B comes out to be 36 times 0.05 over 0.15. So omega B at 2 seconds is equal to 12 radians per second. And likewise, the position of gear B after 2 seconds is equal to 46.4 times 0.05 over 0.15. That is 15.5 radians. This concludes 16.1 through 16.3, planar rigid body motion, translation, rotation. Next up is 16.4, absolute motion analysis.